Okay, let's go for the second part of the session that we have today. We discussed about different levels of, let's say, arousal and different levels of awareness, from completely awake, awake but resting, sleeping, deep sleep. And we discussed that with different levels of arousal, we can have different brain waves that could be recorded with EEG. And they could be in the beta band or even gamma band. They could be in alpha band, theta band, or delta band. And we discussed about these, let's say, D tab in terms of delta, theta, alpha, beta, and how these bands are related to different levels of arousal, and how arousal is basically something like basic building block, initial building blocks of attentional processing. And I will tell you how it is going to be related to attention. We discussed about attention from, let's say, the top-down view and how different areas are involved in top-down attentional processing. We have also discussed about bottom-up attentional processing and discussed about, let's say, areas like amygdala involved, and engage our attention from top down and engage visual processing and auditory processing, somatosensory processing, and then activate from bottom to down, bottom to up, kind of other brain areas like frontal, parietal, limbic structure. So we discussed about these pieces. But in reality, we need to be kind of awake. And wakefulness is going to be important in terms of having all these processes. So if you're asleep, probably none of those things are going to work. And this is the way that we have the general, let's say, tone of consciousness that we have, that we call that arousal. And for that, we have what we call ascending reticular activation system, or AROS, or sometimes just ROS, reticular activation system. That this system, with some kind of brain chemical, would help us to keep things here going on and keep us awake, and with enough level of arousal to be able to engage these functions. Without that, these functions are not going to work. So we need to think about arousal as a part of the attentional processing. Without being aroused enough, the attention would not working, whether it's top-down attention or bottom-up attention. So that is going to be important to take into account. And as I told you, there are some brain chemicals that are involved. And among those brain chemicals, I want to kind of put emphasis mainly on what we call neuroadrenaline. You probably have heard about that. We call neuroadrenaline. And neuroadrenaline, or neuroepinephrine, it is a specific kind of chemical that mainly produced in the brain is what we call leukosterolose. And I mean, there is a kind of long history behind it. I'm not going to discuss about that. But that part of, let's say, brain stem is making neuroadrenergic neurons that would be reflected in many other parts of the brain. And that part of the brain is arranging the level of arousal. And if we have, for example, in something like pathologic state, for example, those who are opioid users, if they stop using opioid, they have a high level of arousal. They would say to you that I'm anxious, I'm agitated, I'm just sweating, I'm just kind of feeling really bad, I cannot just sit still in my place. That high level of arousal are being mediated by these neurons in leukosterolose. So if you give them any specific medication like clonidine, that's suppressing neuroadrenergic production in leukosterolose, clonidine would just technically reduce the level of high abnormal arousal that these people are experiencing in the withdrawal process. Okay? But it's interesting that if you give them clonidine, clonidine is not controlling, let's say, other cognitive aspects of drug use, in terms of they still have drug craving, they still have attentional so they still have other cognitive components of drug addiction in terms of memories, all the habits, all the things that we have discussed. But the arousal would be gone if we give them clonidine, because clonidine would control that. But technically having this system that is controlling something like the general light that we have in the room. If the light is gone, nothing would be happening. But if you have a little bit of light, and then the higher level of light would make things possible in terms of the processes that are going to happen inside the brain. So thinking about arousal as an important, let's say, mediator or component that would contribute to the attentional processing. And if you have high level of arousal, lower level of arousal, then our attentional processing would be different in both top-down and bottom of attention. Okay, so that is a message in terms of the importance of arousal. And how arousal is being mediated by the brain in terms of the different parts of the brain that are engaged. First of all, you need to know that, and we discussed about that before, in terms of we have a really important brain part in the deep into the brain that we call thalamus. And thalamus is connected to almost every single part of the cortex, okay? And thalamus is technically organizing what is happening in the cortex and keep the cortex working on, keep the cortex remain active. So just basically something like the lead of the orchestrate or the person who is kind of directing others to do their own job. And for being able to do that, there are some specific neural circuits in thalamus, a specific part that is around thalamus, but it is not a part of thalamus, but it's another kind of component around thalamus that we call thalamus reticular nucleus. Or nucleus. Okay? And then we have cortex. And these three neurons, as you can see here, neurons from reticular nucleus, neurons that are in cortex, and neurons that are in thalamus. And they make something like a circuit that is active all the time. And this is going up and down, and the current that is going in this system like this. And this is what is making basically the EEG waves that we have. And if the system is working like this, then you have kind of beta wave, theta waves. If the system is doing something like this, then you have, let's say, alpha and then delta and those kind of lower frequency bands. And if I want to just show you the reality of what we have, this is a kind of a representation from a cat brain. This is the cortex, the neuron in the cortex, and then neuron in the thalamus, neuron in the reticular formation, in the reticular thalamus reticular nucleus here. As you can see, they make a circuit like this. And they just basically synchronize. So this one activates this one activates the other one, and then vice versa. So they just kind of keep each other activated. And that activation is the source of maintaining the arousal that we have. If we just turn off the system or just block the thalamus, then the cortex would just get down and the arousal would be gone. And the arousal and the consciousness. So that is an important part in terms of, it seems that when all these pieces are working together, we are conscious. And when these pieces are not working together, they are not coherent by thalamus, we would not be conscious. So if you have a stroke in thalamus, probably you would lose your consciousness. So without your thalamus working hardly to be able to maintain the synchronization and activities in the cortex, your consciousness would be gone. There are parts of the brain that if you lose them in something like a stroke or a trauma, you would basically just lose those functions that are related to that part of the brain. Let's say if you lose the Broca area, you would not be able to talk. If you use your Wernicke area, you would not be able to understand what people are talking about. If you use your primary visual cortex, you would not be able to process some basic visual processing. But there are pieces in the brain, if you lose them, you would lose everything. Basically, it's something like a power in the system. everything would shut down. So if you have a stroke in your thalamus, and the stroke would be in the size that would cover almost the entire thalamus, your consciousness would be gone. So you would go to coma. So there is no consciousness. You can have consciousness without your visual cortex. You can have consciousness without many parts of the cortex. But without having the thalamus, you would not have any level of consciousness. So the thalamus is gone, the consciousness would not be there anymore. And just to give you a sense about how, let's say, different states of consciousness, if we just record neurons in the cortex and try to see, even with just recording from neurons in the cortex, try to see whether people are wakeful in the what we call slow wave sleep, or in the rapid eye movement sleep. So they're still asleep and they are dreaming here. So if we basically record neurons and try to see, based on the recording that you have, in terms of, let's say, beta wave or gamma wave powers in their power spectrum analysis, people realize that even with this kind of measurement and recording, they can differentiate whether people are in this state, or this state. And what you have here is basically the classification accuracy in terms of how many times this system is going to correctly decide whether the organism is wakeful, in deep sleep, or in REM. So this is basically a classification analysis, and those who are from the machine learning side, they know that is simple to do. Not simple to do, but it's just something that routine that people are doing. And these are neurons in basal forebrain. I'm not sure about what was VC, but I can double check that. But it probably says ventral tegmentum, or I'm not sure. I can double check. So if we record things in the basal forebrain, this is the kind of the recording in animal models. If we record them for 15 seconds, or even we record them for 3 seconds, even with recording for 3 seconds from neurons, with something like 80% of accuracy, we can tell whether the animal is awake, in slow wave sleep, or REM. And this is the discrimination space. So technically we can, even with recording kind of few neurons, we are able to see whether the neurons are awake, whether the animal, the kind of the entire animal, the animal being by him or herself, is awake. And when the animal is awake, you can have, let's say, activation in a wide range of different kind of levels of beta and gamma power. But those who are in the slow wave sleep are limited, so that the activation, the variation would be much limited. And those who are in the REM, the activation would be limited as well. The bottom kind of down message of the entire, let's say, slide that I'm showing is that technically, even with recording few neurons in the cortex of an animal, without having any idea about what animal is doing, you can accurately say that whether the animal is awake, sleep, and in what phase of a sleep, basically in the deep sleep or in the REM sleep. And that is important in terms of, it is not very important in terms of where you are recording from the cortex, whether you are recording from the basal forebrain, you are recording in other parts of the cortex. It is going to be almost the same in terms of a general recording from the neurons in the cortex would give you a sense in terms of whether the animal is in something like which state of consciousness, if we name that as we are discussing. That is going to be something that we can differentiate with just recording from few neurons. It is not something that is related to, let's say, one specific part of the cortex. It is something that is related to the entire cortex, whether we are in, let's say, wakeful situation or we are in deep sleep. So even with few neurons, that is going to be defined. And just going back to the slide that I showed you in the first place, when I talk about, let's say, EEG, you need to always say that, okay, if it is a recording, is this recorded from, basically I need to define the electrode that I'm recording from. Is it a recording from the frontal side, is it the recording from the parietal side, is it a recording from the occipital side? Technically, they do not report that for these figures because wherever you record, it is going to be the same in terms of differentiating between different level of kind of arousal. And that is the reason that, I mean, they just report, I mean, whatever electrode, whether it's F3 electrode or F4 electrode or OZ electrode, whatever the electrode that you are recording, the pattern would be the same because that is the general response that you have in the entire cortex. It is not related to one single part of the cortex. If let's say, the thalamocortical loop is down and your consciousness goes to the specific state of sleep, whatever that is happening around the entire cortex is going to be almost the same. Okay. The last piece that is important here to mention about the role of hippocampus in this circuit. So other than, let's say, thalamocortical, we also have hippocampus in this pathway. And why hippocampus is playing a significant role here, and how this interaction between cortex, hippocampus, and thalamus is making different stages of sleep and would contribute to different types of dreams that we can see, and meanwhile contribute to the process of learning and encoding information and consolidating information inside your brain. That is a target for chapter 12 or session 12, and I will cover that in that session. So we will discuss about sleep and levels of consciousness in that kind of chapter and that kind of part of the discussion. So if you keep on kind of attending the class, we will discuss about those features later on that part of the class. Okay, that was the end of the part 2.